Hi everyone, and welcome to my video here where I'm going to tell you about my project looking at the geography of numerical mixing in a suite of global ocean models. So this is currently in review at James. And what I'm going to give you here in this video is just a really brief kind of overview. I'm not going to have time to go into any of the details. I really encourage you, if you're interested in those details, to have a look at the preprint, which is available. So you should be able to get that by just Googling the title here. And so before I get started, just like to thank my collaborators, so Jan Zieker and Matthew England at the University of New South Wales in Australia, Steve Griffiths from GFDL, and Andrew Hogg and Andrew Kiss from ANU. Okay, so just a brief introduction. What is numerical mixing? Well, I define it here as the artificial or spurious diffusion of tracer gradients arising from discrete advection. So if we have a really simple example, a continuous one-dimensional advection equation for a tracer theta, so velocity u in the x direction. If we discretize that equation using a very simple centered in space, backward in time, finite difference, and we do a Taylor series expansion, we figure out that the equation that we're actually solving is this one, where the leading first order, the leading error truncation term is a diffusion term. So this is numerical diffusion. So basically says that we're setting out to solve an advection equation, but instead of just getting advection, which would just shift this shape to the right, we also get diffusion, which kind of mixes it with its surroundings. Now, obviously, real models are much more sophisticated than this. They use more sophisticated advection schemes, but numerical mixing is still known to contribute to model bias. It's still an issue. And a kind of well-known saying is that, particularly for coarse resolution models, the models mix too much. And this is particularly a problem in the ocean because we know that in the interior of the ocean, there's very weak mixing. The dipictal diffusivity is small, and this numerical mixing in these models can often be much larger, causing problems. Now, one problem with this, which we're going to address in this project, is it's very difficult to quantify numerical mixing in realistic models. Typically, it's just studied in idealized contexts. So what we're going to do here is I'm going to present to you a new method for quantifying the spatial structure of numerical mixing. We're going to focus on temperature here in realistic global ocean models. It's the key advance there. And we're going to look at the sensitivity to model resolution and physical parameterizations. And I want to point out that we're not going to look, unlike a lot of these idealized studies, we're not going to test sensitivity to the advection scheme. We're just going to take the advection scheme of this particular model, which I'll describe in the next slide, as given, and just see what its implications are. And we're also not going to be able to decompose, because we're going to focus on temperature, we're not going to be able to decompose the isopycnal and dipycnal components of numerical mixing, just because it's a bit more difficult. That's something we want to do in the future. So we're going to apply this to a model. This is the Australian Community Ocean and Sea Ice model. It's basically MOM 5.1 coupled to SICE 5.1, and we're just using some climatological forcing. And the model is available at 3 different resolutions: a 1 degree coarse, non-eddy resolving version, a 1/4 degree eddy permitting version, and a 10th degree eddy resolving version. I'm not going to go through these in details. One important kind of thing to point out is that the advection scheme we're using for traces, particularly temperature, is the multidimensional piecewise parabolic method, and we have flux limiters. So the facts that we have flux limiters on this advection scheme means we prevent the formation of extrema in the tracer distribution, meaning we have to have some diffusion. So it's a diffusive, we can think of it as a diffusive advection scheme. And we're going to look at the sensitivity to a bunch of different parameters: so horizontal resolution, neutral physics parameterizations, vertical resolution, and background vertical diffusivity. But I'll spend a bit of time talking mainly about a control simulation, which is a 1/4 degree simulation with with very weak kind of physical diffusion parameters, which I'll go into in a bit more detail in a second. The method we're going to use, again, I don't have time to go into the details of this too much. It's basically based on the water mass transformation framework. We construct the heat budget for layers, for temperature layers in the ocean. So if this is an isotherm, say the 15 degrees Celsius isotherm, we construct the heat budget for all of the water warmer than that temperature in the ocean. So obviously in the tropics and at the surface. And we calculate all of the other terms that can contribute to that heat budget, say surface forcing, explicitly parameterized vertical mixing and along isopycnal mixing, the tendency term, and we can back out the numerical mixing as a residual. Now there's some details about how we do this. We can kind of get some advantage by combining it with the volume budget, which I've described a bit more in this paper, which gives us more robust results. And we're doing all of our budget terms online. So we're doing our binning of our kind of online heat budget terms into temperature coordinates online. So we capture all the temporal variability. Again, please have a look at the preprint if you're interested in more details. So here's a picture of what we get for this. So this is, you can think of, we get a value for each isotherm in the ocean. So we've got temperature here on the x-axis. What I'm showing you is heat transport in temperature coordinates due to each of these different terms. So the positive term, this is kind of a positive heat flux in temperature coordinates, is an upgrade in heat flux. So that's acting to increase temperature contrast in the ocean. So that's what surface forcing does, which is the black curve. So that makes warm water warm and cold water cold. And to balance that, we have our mixing terms, which flux heat down gradient, so to the left. And in this particular case, we have, so vertical mixing is in red, and then blue is what we infer by residual as numerical mixing. And so what you see is that the warm to cold heat transport associated with numerical mixing really exceeds that associated with vertical mixing in this particular configuration, which, as I mentioned before, has really weak or quite weak explicit mixing. So there's no long isopycnal mixing here, and there's no background vertical diffusivity. So we'll look at that in a bit more detail. But you can see it's clearly playing a pretty big role in this model. Now we can extend that. This is really a global measure. We get one measure of numerical mixing for each temperature, but globally integrated. We can extend this method to look at the spatial structure by basically applying the same idea, but to a single fluid column. So that's what I've got here. The extra information we need to introduce to do that properly is the lateral volume and heat fluxes. So it's the J and the Q here. We bin them again online into temperature coordinates to capture all the temporal variability. There's a few more approximations we have to make, but in reality, it works pretty well. And again, I'll refer you to the preprint to look at some of those details. So what we can do then is, let's say, go to the 22.5 degrees Celsius isotherm here. So it's basically near the peak where the numerical mixing is strongest in a global average. And we can look at the spatial structure. So this is the heat flux in watts per square meter through that 22.5 degrees Celsius isotherm in the simulation as a spatial map. So you can see it's pretty heterogeneous. We've got hotspots, say, in the eastern equatorial Pacific here, in the tropical regions, and also some in the kind of western boundary currents and along the continental shelves. If we zoom in this kind of longitude depth slice in the eastern or in the Pacific here, that's what I'm plotting on the left here. So this is numerical mixing as a function of depth. It's actually calculated in temperature coordinates, remapped to depth. And then on right, for comparison, I'm showing the explicitly parameterized vertical mixing. And so you can see numerical mixing is kind of strongest where we've got really strong vertical temperature gradients in this far eastern Pacific region here. There's also strong horizontal velocity variability here, so it's kind of suggestive of where the numerical mixing is coming from. There's a lot of noise at the grid scale, and the grid is really struggling to resolve those temperature gradients. There's also strong numerical mixing above the thermocline. Again, in this region, there's strong velocity variability and temperature variability associated with things like tropical instability waves. And again, you can see that numerical mixing is pretty comparable to vertical mixing, particularly in this Eastern Pacific kind of region. Now, I'm not going to go into detail about our kind of sensitivity to parameters, but in this equatorial region, it's particularly sensitive to vertical resolution. So we compared a bunch of different vertical resolutions in the 1 degree version of the model. Here's just an example where we've got 50 levels on the left. So again, this is the flux due to numerical mixing, and 135 levels on the right, and you can see you get a reduction. Now, because we're in the tropics here, density is really dominated by temperature, and because it's sensitive to vertical resolution, we really think most of the numerical mixing occurring in this tropical thermocline region is really diapycnal. That's kind of a nice thing to know. And it's important, right? So this impacts on temperature biases. We can see here, when we increase the resolution, we actually reduce, so going 135 levels, we actually reduce temperature biases in the Eastern Pacific. So going on to looking at some cold temperatures. So here we have the 15 degrees Celsius and the 5 degrees Celsius isotherm. You can see the hotspots of numerical mixing in these cases are really the western boundary current regions and the high latitude kind of shelf currents. So this is where there's lots of eddies going on. And you can actually look at that in a little bit more detail. So you can see there's lots of horizontal velocity variability in these regions, a lot of horizontal temperature variability. And so we really think it's more lateral processes that's driving the numerical mixing in these regions, as opposed to in the tropics where it's more vertical. And this kind of begs the question, well, we thought in the tropics it was diapycnal. What about in these regions? We know that eddies drive a lot of long isopycnal mixing. In this particular configuration, we're not parameterizing that explicitly. Is the numerical mixing just kind of taking that role? Again, we can't really answer that question precisely in the study because we don't have a way to decompose those isopycnal and dipycnal components, but we can kind of alter the along isopycnal mixing. So if we introduce explicit along isopycnal mixing, we're going to reduce those along isopycnal gradients and potentially change numerical mixing. And that's indeed what we see. So the bottom panel here is this global heat flux due to numerical mixing. The red configuration is the standard configuration where we don't have any explicit along isopycnal mixing. And then when we introduce explicit along isopycnal mixing, so going to the black dash or dotted line, we see a reduction in numerical mixing by about 60%. At cold temperatures, right, we get very little change at warm temperatures. So this is again suggesting that there is some along isopycnal components to that numerical mixing, but it's not all there, right? So there's still some left there. And we need to do some more work here to try and kind of decompose that in a little bit more detail. Okay, finally, this is the final slide before I get to my summary slide. So the sensitivity to horizontal resolution. So it's generally thought that numerical mixing is relatively small at coarse resolution where you don't have any variability. It gets larger when you start to marginally resolve eddies. So you start getting variability, but it's really near the grid scale. So it's kind of more noise-like. And then it gets smaller again as you go to higher resolution. And this is indeed the case in kind of standard configurations of these three resolutions. But a lot of this is the differences are potentially linked to differences in physical mixing. So we know that at 1 degree, we generally parameterize a lot more. We have stronger diffusivities. We reduce that as we go down in viscosities. So what we've done here is kind of come up with some more consistent configurations. So I can't get an exact 1/4 degree consistency because of it just doesn't make sense to turn off the mesoscale eddy parameterizations in the 1 degree simulation. But in that case, we do see an increase in numerical mixing when we compare those going to a 1/4 degree. Comparing 1/4 degree and 10th degree configurations, now these two are actually, all of the parameters are the same except for the horizontal resolution and the fact that the viscosity, the lateral viscosity is grid scale dependent. So that reduces as you go to 10th degree. And what we see there is a slight reduction in numerical mixing, so consistent with this idea here as we go to a 10th degree. But I want to point out that if we do another simulation where we actually keep the horizontal viscosity constant, then we see a much stronger reduction. And so this is kind of moving towards numerical convergence. If you keep your viscosity the same, you're going to kind of reduce and you better resolve those velocity gradients with a higher resolution grid. You're going to reduce your numerical mixing. Okay, so just to summarize, basically I've put together a new method for quantifying numerical mixing. And the key point is it's in realistic models and gives us an idea of the spatial structure. Applied this to a suite of Axis OM2 simulations. Conclusions, we've seen that numerical mixing is pretty significant in these models. It drives a large fraction of the global warm to cold heat transport. I summarize that in a diagram on the right here. So basically the y-axis is a measure of the total amount of numerical mixing in its configuration, and the x-axis is the explicit mixing. I have 13 different configurations here. Anything that lies above this dashed line is telling us that there's more numerical mixing on average than explicit mixing. And so you can see that's the case for some of these configurations. We've seen that the hotspots for this numerical mixing are really in the tropical thermocline and the eddying western boundary currents. We've seen that numerical mixing is sensitive to resolution and explicit mixing parameterizations. And that you can kind of see in this diagram. And it kind of raises some interesting philosophical questions. So you might see that a lot of these kind of configurations lie on a line, which indicates if you have stronger numerical mixing, you have weaker explicit mixing, or vice versa. And so it kind of opens the question, we can kind of move along this line, and there might be reasons we might want to have more numerical mixing, so overall we get less numerical mixing. But the question is, does numerical mixing constitute a valid representation of absent physical mixing? So that's an interesting question. Obviously, some future work here, we'd really like to be able to decompose the dipycnal and isopycnal components. So that's it. Please check out the preprint if you'd like more information, and I'm happy to answer any questions via email or suggestions. Thank you.